Hey everyone, and welcome back to the Explainer for the Foundry by Forge College. Now, if you were hanging out with us for our previous lesson, evaluating performance and scalability, you know we just finished building the software equivalent of a blazing fast, highly optimized sports car. I mean, we tuned the engine, we reduced the drag, the whole shebang. It is absolutely ready for the track. But today? Well, today we actually need to talk about what happens when you drive that sports car out into the real world. We've got to make sure it doesn't just smash into a brick wall the very first time the network blips. So today, we are mastering reliability and error handling in your deployment scripts. Here's our survival guide for transforming those stressful, cross-your-fingers deployments into robust operations you can actually trust. We're going to cover 1. The deployment danger zone. 2. The magic of idempotency. 3. Handling network hiccups. 4. Saving your deployment state. And 5. Building bulletproof scripts. Let's jump in. Section 1. The deployment danger zone, when automation fails. Okay, so what actually happens when your continuous integration runner aborts mid-deploy? Let's be real, it is the universal developer experience, right? You're sitting there, staring unblinking at a terminal screen, essentially just trying to bribe the Web3 gods to let your transaction mine. And then, bam, the node times out, or your CI connection just flat out drops. And you're left holding your breath, wondering if your contracts actually made it to the blockchain, or if they're just, lost forever in the digital ether. Let's identify the true villains of your deployment process here. Looking at the first row, we've got the duplicate deployment. The symptom? Well, you end up with multiple contract instances on-chain when you only expected one. The root cause here is blindly deploying without checking the current state. And the real-world pain? You're paying Ethereum gas fees twice, which, let's face it, is a surefire way to drain your project's treasury and your will to live. Then, down on the second row, we have the dreaded partial deployment. This is where some contracts deployed successfully, but vital configs are completely missing. Why? Because there's no rollback or state awareness built into your script. You are essentially stranded in this broken, half-finished state that is just an absolute nightmare to debug. Section 2. The magic of impotency, your video game's save point. So what is idempotency? It means that running the exact same script multiple times produces the exact same final state. No duplicate contracts, no duplicate records, no partially applied updates. Think of it exactly like a video game save point. If you beat a really difficult boss and hit the save point, mashing save 5 more times doesn't spawn 5 more bosses, right? It doesn't skip you ahead 5 levels. No matter how many times you interact with it, it recognizes where you are and it doesn't duplicate your progress. Your deployment scripts need to act exactly like that save point. This brilliantly illustrates the difference in practice. Over on the left, we have what we call the naive script. It fetches the contract factory, deploys blindly, and unconditionally logs the address. It basically just guesses and hopes for the best every single time you hit run. But on the right side, the idempotent script. This one is smart. It actually checks for an existing deployment artifact file first. If it finds one, it either bails out entirely, or it intelligently reuses the existing address. It looks before it leaps. This is literally the fundamental difference between a script that causes you weekend headaches and a script you can actually trust to run automatically. Section 3. Handling network hiccups. Don't pound on the door. Okay, to handle those transient RPC errors gracefully, we implement something called exponential backoff. It's a retry strategy that waits progressively longer between each attempt to recover from exceptions. Imagine you go to a friend's house and knock on the front door. If they don't answer immediately, you don't just frantically pound your fists on the wood 50 times a second, do you? That's just gonna break the door or get you yelled at. Instead, you knock, wait a moment, knock again, wait a little longer. That is exactly how your deployment scripts should interact with an RPC node. Let's see how this builds mathematically. Step 1, wait 200 milliseconds. Step 2, wait 400 milliseconds. Step 3, wait 800 milliseconds. See what's happening? The delay doubles each time. What we're doing here is creating a lightweight retry helper that catches transient exceptions and intentionally pauses before reattempting. This gives the network a chance to breathe and recover. It drastically reduces failures from temporary node blips without instantly flooding the network, which, by the way, is exactly what causes duplicate state when your first attempt actually succeeded, but the response was just temporarily lost. Section 4. Saving your deployment state. The proof of work. So, to make both idempotency and exponential backoff work flawlessly together, your script needs a reliable way to prove what's already been done. And that brings us to the verification artifact. It's essentially a structured JSON format file acting as your receipt. It stores your deployed contract addresses, your transaction hashes, and simple status fields. Just as a quick aside, learning how to properly generate and manage these exact artifacts is a core part of the broader Web3 engineering programs and courses taught at Forge College. It's truly one of those foundational operational skills that instantly separates amateur coders from professional systems engineers. The vital components of this machine-readable deploy artifact file include your deployed contract addresses, your transaction hashes, and your checksums, or status markers, like a really simple field stating deployed, true. We absolutely need these elements explicitly written down so that your downstream automation and CI runners can instantly verify success just by parsing this one single file. Now, I want you to pay close attention to this highlighted line of code right here. Provider.transactionReceipt.tx hash. This is your ultimate safety net. We only, and I mean literally only, write the artifact to our file system after we use this command to confirm on-chain mining. Think about it. If you write the artifact before the transaction is definitively mined and your node crashes, you end up with a false receipt and a partial state. You must always wait for the blockchain itself to give you the official, verifiable thumbs up. Section 5. Building bulletproof scripts. Pulling it all together. Adopting these core resumable operation habits is absolutely crucial. First, always write machine-readable deployment artifacts. Second, aggressively check prior state before creating new resources on-chain. Third, implement controlled retry with exponential backoff. And fourth, emit structured exit codes on irrecoverable failures so your CI knows exactly what went wrong. Adopting these habits is what transforms chaotic, anxiety-inducing deployments into predictable, boring, resumable operations. And trust me on this, when you are deploying smart contracts holding real value, boring is exactly what you are aiming for. Before we wrap up, I want to leave you with one final, kind of provocative thought. Are your deployment artifacts accidentally exposing sensitive private keys in your logs? It's a scary thought, isn't it? Well, mastering today's reliability fixes perfectly sets the stage for our very next lesson on deployment security fundamentals, where we'll tackle secret handling and signer policies head-on. To continue this journey, analyze your own repositories, and explore more advanced Web3 topics, make sure you visit forge.college. Thank you so much for joining me on this explainer, and I will see you next time.